So tonight's lecture is on geothermal energy and heat pumps. There are two types of geothermal energy. Geothermal energy is basically using the heat that's kind of inherent in the earth, and there's two ways in which to use that. Low temperature geothermal energy uses the steady temperature of the earth a few meters deep in the ground or in a body of water. It can either be in the ground or in the water. Usually it's around 55 degrees in this latitude for heating and cooling. It's essentially kind of the average annual temperature. And it usually requires a heat pump because 55 degrees isn't really cold enough for cooling in the summer or heating in the winter. Although at the Eco Village we do use the temperature of the ground in very simple geothermal systems directly, which I think I'll explain more in class than in this video. But it's a way you can very simply and directly use the steady, stable temperature of the earth for heating and cooling. But typically it requires a heat pump. So in this lecture we'll also talk about how heat pumps work. Then high temperature geothermal uses the high temperature that's deep in the earth to make steam and generate electricity. So this is high quality, highly orderly form of energy versus the lower quality, low temperature geothermal. In special places like near volcanoes and hot springs, high temperature heat can be actually very close to the surface, but typically in most places it's very deep in the earth, several kilometers. So here's and again, I'm going to play a little video for you, and what you want to consider here is this is actually a product promotion video. So put your critical thinking cap on, and we'll discuss some of the claims they make in this video a little bit more later.
What if there was an abundant source of free, renewable energy that could be used to heat a house in the winter, cool it in the summer, and provide hot water all year round? Well, a growing number of homeowners say there is, and it's powered by the sun. While you may be picturing solar panels, these homeowners are actually talking about geothermal. If you're a typical homeowner, almost 2/3 of your total energy bill is for heating, cooling, and hot water. The rest is for lighting, appliances, and other usage. That means the biggest opportunity to save money on your energy bill is to increase the efficiency of your heating, cooling, and hot water system. A geothermal heat pump taps into the renewable solar energy stored in the ground to provide savings of up to 70% on utility bills. Although it operates similarly to a standard heat pump, a geothermal heat pump exchanges heat with the earth instead of the outdoor air. Outdoor air temperatures can vary greatly from day to night or from winter to summer, while the temperature just a few feet below the Earth's surface stays an average 55 degrees to 70 degrees Fahrenheit year-round. To see why that's so important, let's look at traditional conditioning systems. In order to cool your home, an ordinary system collects indoor heat and expels it outside. Unfortunately, summer temperatures can easily hit 90 or 100 degrees, which means outdoor air already is filled with heat and is less willing to accept more. The exchange process becomes harder and harder. The result is that an ordinary heat pump or air conditioner becomes least efficient at exactly the time you need it to be the most efficient. A geothermal unit never sees hot summer air. It collects heat from your home and moves it to the much cooler 55-degree Earth. It doesn't matter how much outdoor conditions fluctuate, the ground remains relatively constant. Thanks to the constant temperature of the Earth, a geothermal heat pump is more than twice as efficient at cooling than any regular heat pump or air conditioner. To warm your home, an ordinary heat pump reverses to collect outdoor heat from the air and move it indoors. Unfortunately, as winter temperatures drop, there's less and less available heat to collect. Again, the exchange process becomes harder, and the heat pump becomes least efficient at exactly the time you need it to be the most efficient. A geothermal unit never sees cold winter air. It draws from a reservoir of much warmer 55-degree temperatures, concentrates it, and moves it to your home. And unlike a traditional furnace, which returns less than 96 cents of heat for each dollar spent burning expensive, polluting fossil fuel, a geothermal heat pump returns up to $5 of heat for each dollar spent on electricity. That's because, unlike a furnace, a geothermal heat pump doesn't create heat through combustion. It simply collects and moves it. Now that you know the benefits of using the earth, let's look at how it's accomplished. A geothermal system uses a series of underground pipes called a loop. The earth loop eliminates the need for fossil fuel. It's the heart of a geothermal system and its biggest advantage over ordinary heating and cooling technologies. Closed loop systems circulate a water-based solution through a collection of small diameter, high density, polyethylene underground pipes. There are three main types of closed loop systems. Where space is limited, vertical loops are used. Well drilling equipment is used to bore small diameter holes from 100 to 400 feet deep. Horizontal loops are generally preferred where more space is available. Pipes are placed in trenches that range in length from 100 to 400 feet. If a nearby body of water is available, it can be utilized for a pond loop. Coils of pipe are simply placed on the bottom of a pond or lake to capture the geothermal energy. Open loop systems are an option if water is plentiful and low in minerals. These systems use groundwater from a well as a direct energy source. Water furnace dealers and loop installers are trained to design the best loop system for a particular home to ensure optimum performance. You've learned that a water furnace system lowers bills dramatically by using the stored solar energy in the ground. You've also learned how the system works. Now, let's look at its other benefits. Water furnace geothermal systems are recognized by the United States Environmental Protection Agency as the most environmentally friendly, cost-effective, and energy-efficient heating and cooling technology available. Geothermal heat pumps help electric utilities achieve significant reductions in their peak demand loads. By reducing the demand on electric utilities, geothermal systems reduce the need for new power plants, which typically are powered by coal or natural gas. Compared to an electric resistance heating system, a typical 2,500 square foot home with a geothermal system can save the electric utility company more than 9 tons of coal a year. These systems also minimize the threat of acid rain, air pollution, the greenhouse effect, and global warming, problems directly linked to the burning of fossil fuels. In fact, installing a single geothermal unit is the environmental equivalent of planting 750 trees or removing 2 cars from the road. As you can see, there are many reasons to switch to a water furnace geothermal heat pump. It's the most efficient conditioning system available. It's environmentally friendly. It has the longest lifespan, and it provides quiet comfort. That's why we call it smarter from the ground up. For additional information about the benefits of a geothermal heating and cooling system, visit waterfurnace.com or contact your local water furnace.
So there you have the miraculous benefits of geothermal heat pumps, and we'll talk about in a little more detail about how a heat pump works, and then kind of dissect some of those claims that they made in that video. You notice they didn't say anything about the total amount of energy you need in your house or the cost of that system. And so we'll talk, about that. In other words, if you can minimize the amount of energy you need in your house, then you don't need a big, expensive system that can produce tons and tons of energy from the ground. You just need a little tiny amount of energy, and a big geothermal system for a typical house might cost $15,000 or $20,000, and it requires a lot of electricity. It multiplies the benefit, the capability of that electricity to heat. If you use it directly in resistance heating compared to running in a geothermal system, it might be 2 or 3 to 1. So for every 1 unit of electricity you put into an electric resistance heater, you get 1 unit of heat out. But if you put 1 unit of electricity into a ground source heat pump system, you'll get maybe 2 to 3 units of heat out of the system. But that's still 1/3 of the energy that you need to heat your house is going to have to come from electricity from somewhere. And it's going to have to come from electricity in kind of the worst time of the year, when it's really cold, or sometimes when it's really hot. So we'll talk a little bit more about that later, but let's talk about how heat pump systems work. So air conditioners, refrigerators, heat pumps, they all work under the same principle. And we can start anywhere in this system. Let's start here, where we're taking warm air and we're we're creating cooler air by taking a liquid here and it is a liquid that boils at a very low temperature. Let's say that it boils at, it's under the conditions where it boils at a low temperature. Let's say it boils at 80 degrees Fahrenheit. Well, when it boils, it extracts. Remember the phase change when something changes from a liquid to a gas, it absorbs a lot of energy. So it's going to absorb a lot of energy, and it's going to become cold. So this is the evaporator, where we're boiling this fluid with the warm air in the room and producing cold air. Then, so that's now, instead of being a liquid, it's now a vapor. It's boiled, and then we run that through a compressor and put it under high pressure. So now we've got a vapor that's under high pressure. And what we do with that in that situation then is that it's going to be hot, and a vapor that's warmed up and hot, it's going to be hot. So it's going to be hotter than, for example, the temperature outside. Let's say the temperature outside is 90 degrees, but this is 110 degrees. So you take this, and now what you've got a vapor at 110 degrees, excuse me, going into the atmosphere at 80 degrees, and that's going to condense on this condenser. It's going to go from a vapor to a liquid. And remember, when something condenses, when something goes from a gas state to a liquid state, it gives off a lot of energy. So it's going to take the energy it picked up here and drop it off here and dump it out into, let's say, the atmosphere. Let's say this is a cooling situation in your house, and you want to cool your house. You've got warm air, you bring cold air, producing cold air in this part of the system, and then over here you're taking that heat that you took out of the air, and you're going to dump it out into the environment at a higher temperature. So this is a way in which, remember, heat typically always flows from warm to cold. In every place in the system, the heat is flowing from warm to cold. It's just that because of the way we've arranged things, we can actually get heat to flow from inside a building to outside where it's actually hotter in the summertime. So we've gone, now we're in the condenser, and we're condensing this high temperature liquid after we've compressed it. We're condensing it, and it's become a liquid again, and it's coming out of this condenser as a liquid. And then what we do is put it through an expansion valve, and this is kind of where the magic happens. And so what you can think of as an expansion valve is it's sort of like if you take an aerosol spray can, like a can of whipped cream, or a can of air that you use to clean your computer with. You press on that, you notice it gets really, really cold right where your finger's pressing on it, because what happens when fluids under pressure expand into a low pressure area, they get cold, they absorb energy, and so it cools the surroundings. So what's happening here then is that we're going to expand that liquid, and we're going to change it from a liquid now. We're going to expand that liquid, and it's going to become a liquid and a vapor. Now, partly a vapor as we expand it through this valve, like we would expand it under, because it's under high pressure on this side. It's going to be under lower pressure here, and it's going to be partly a liquid and partly a vapor. And it's going to now be ready to go, and it's going to have dropped its heat off here. It's going to be cooler, and it's going to be ready to go up into this area here and collect heat again, and then the whole process starts again. So we'll go over this again in a second, but this is the basic principle for how a refrigerator or a heat pump works. Now, there's another one of these kind of surprising things that comes out of the second law of thermodynamics. We don't have the time to sort of derive this, but it turns out that that there's a maximum efficiency at which this process occurs. And essentially, if you look at sort of an abstract block diagram of what we're doing, is we're putting work into it. We've got a hot reservoir and a cold reservoir. So the hot reservoir, for example, is in an air conditioner, is the atmosphere outside, and the cold reservoir is the cooler temperature in your house. And what we're doing is we're putting work into the system, and we're moving heat from someplace where it's cold to someplace where it's warmer. And this actually, let's think about this a little differently. Rather than think of this as an air conditioner, let's think of this cold reservoir as the air outside in the wintertime, and the hot reservoir as, which might be 30 or 40 degrees, and the hot reservoir as the 70-degree temperature of your house. And what you're doing here is you're putting work into this system and you're moving heat from the atmosphere into that's at a colder temperature into your house that's at a hotter temperature. And the maximum efficiency of this turns out it's not related to the arrangement of the machinery or the fluids you use or any flux capacitors or magnets or any other kind of esoteric technology. It's strictly related to the temperature of the hot reservoir divided by the temperature of the hot reservoir minus the temperature of the cold reservoir, and these temperatures have to be in absolute degrees. So in the case of Fahrenheit, that's the Fahrenheit degrees plus 460, and which makes it into degrees Rankine. So you can calculate the maximum efficiency you could ever get out of this heat pump in moving heat from where it's cold outside or maybe in the ground, 55 degrees, where you want to move it into your house. And here's where the advantage of a ground source heat pump comes, because you notice what happens here is that the colder it gets, the bigger this number is. And so as the outside, and then that makes the overall efficiency lower. So as the outside temperature drops, as the temperature difference that you're kind of trying to move this heat from cold to hot gets larger and larger and larger, you have to put more and more and more work in, and you get less of a gain. So at modest temperatures, let's say 40, 50 degrees, 30 degrees, with conventional kind of heat pumps, you can get a gain of 2 or 3 to 1 practically from moving heat from the atmosphere or the ground into your house. But as that temperature drops, there becomes a temperature at which it takes all the energy you're putting in is essentially you're not able to really move. All the energy you're putting in is turning into heat and in the hot reservoir, but you're not really moving any heat here. And so at some point, this coefficient of performance becomes 1, which means you put 1 unit of energy in and you get 1 unit of energy out, which is essentially the same as what an electric resistance heater does. So at some point, at some cold temperature point outside, a heat pump will stop working effectively. Now, there's been so that's the great advantage with using a ground source heat pump, because the ground stays at 55, and therefore the coefficient of performance, even if it gets very cold outside in the air, can stay really high because the heat pump is working against a 55 degree ground cold reservoir instead of a 20 degree below zero cold reservoir outside. And so that's the big magic trick with ground source heat pumps. Now, again, there's been a revolution in this technology, and it turns out that now you can have air source heat pumps, meaning you don't have to put all the pipes in the ground, and they have coefficients of performance that are as good or better than ground source heat pumps, and you can get them in ground source heat pumps. Typically, you can't get really small ones. So if you have a very efficient house, you can't put in an inexpensive ground source heat pump because you've got to put tubes in the ground, and there's a lot of equipment, pipes, pumps to pump fluids into the ground, and it's expensive and somewhat complicated. So on a typical house, this is a $15,000 to $20,000 proposal, and you're still going to use quite a lot of electricity. You're going to use a third of the energy for heating your house is going to come from, you're going to have to buy from the power company. So but with the new kinds of air heat pumps called mini split, what they do is they can have a coefficient of performance of 2 or 3 all the way down to 10 below zero, and it's rarely below 10 below zero in Iowa. So and then those cost for a small, you can buy a small one. You have a very efficient house, you can buy a mini split for $2,000, and then the kilowatt hours you need are fairly small. You're still going to have to buy a third of your kilowatt hours for heating your house, but now it becomes practical to think about, well, how many more solar panels am I going to have to put on my house to offset the annual energy I need for heating and cooling from a mini split, where it would be, because you can make your house really, really efficient to start off with, so you don't need very much energy. And then the mini split's only a couple of $1,000s compared to $15,000 or $20,000 for a ground source heat pump. So again, one of these places where ground source heat pumps were sort of a good idea for a while. In some cases, they still are a good idea if you need a lot of energy. But these mini splits are really taken off and being installed everywhere. Really reliable, fairly simple devices. And here it just talks a little bit more about this coefficient of performance, where essentially that's the energy delivered divided by the energy required. So if you get 100 units of energy delivered and it only takes 50 units of energy to do that, then it's going to give you a coefficient of performance of 2, 100 divided by 50. And the theoretical maximum is always going to be the high temperature that you're collecting, that you're putting the energy into for a heat pump, and then that's going to be divided by the high temperature minus the low temperature reservoir that you're working against. And peak coefficients of performance, when the temperature differential isn't very high, can be as high as 5 or 6. But seasonally, it's usually 2 or 3. Another issue with heat pumps well, I won't get into all the issues with heat pumps. There's many different things to consider. But again, when we talked about, if you keep a building at 70, 75 degrees, with the older style air heat pumps, as you approach 30 degrees Fahrenheit outside, you got to a coefficient of performance of 1, meaning 1 unit of energy in gives you 1 unit of energy out, and it's essentially the same as electric resistance heating. And so you don't really have a gain. But now, with the new technology, this number now is down around 5 degrees or minus 5 degrees or minus 10 degrees. And these can also be used. Heat pumps can be used for heating, and they can also be used for cooling. And the cooling coefficient of performance is a little bit different. So let's not talk about that right now. So I want to point out a consideration on heat pumps if they're being powered by conventional fuels, by fossil fuels. So let's take a look at a situation where we've got 0.9 units of coal energy going into an electrical generating station. Remember we said 2/3 of that is going to go and be dumped into a river or the atmosphere and be thrown away. So that's what's being shown here. And then about 1/3 of that is going to go into electrical energy, which you then put in the heat pump. Now the heat pump is going to take that 0.3 units of electricity and pull 0.7 units out of the ground, and it's going to then put 1 unit of heat back into your house. And so you've done this kind of magic thing where you've taken a 0.3 units of electrical energy and you've been able to move 0.7 units of heat from the ground, and that sounds really great from this perspective. But when you step back and look at the whole system, you started off with 0.9 units of coal, and you get 1 unit of energy into your house. So it's essentially the same. You would have been just as well off to burn the coal in your house directly and eliminate all the complication of the heat pump. So it becomes a really convenient and efficient way to burn coal to heat your house. So with conventional fossil fuels, I never thought that heat pumps made that much sense because of the inefficiency in generating electricity. The efficiency of the heat pump is kind of offset by the inefficiency of the process of making electricity from heat. Here's a case where you burn, like say, 1.4 units of natural gas in a house. You throw away a little bit because furnaces aren't 100% efficient, but some of them are 90% efficient or 95% efficient. This is a older system, 60 to 70% efficient. And it says in this little note down here that you can purchase natural gas furnaces that have over 90% efficiency. So anyway, this is just showing that 1.4 units going into natural gas burning at a house. You throw away a little bit, and then you have 1 unit at the house. Now let's talk a little bit more. Let me just go through, because this is kind of a magic process in some ways, and I want to go through this process of how the heat pump heating cycle and cooling cycle both work. So let's start in a situation where we're heating, and heating means we're going to take heat from, and we're going to move heat from the outside where it's colder into your house where it's warmer. We're going to move heat where it doesn't want to go. And the way we do this is we start with an evaporator. So this is going to be a fluid that boils at a low temperature. So, no, excuse me, this is going to be a fluid that boils at a low temperature. No, yes. So we're going to have this fluid come in here, and it is going to, oh, no, excuse me, this is going to, yeah, that's going to boil at a low temperature, and it's going to absorb heat as it takes heat to boil that, evaporate that fluid. This is right. and turn it into a liquid, into a gas. So you've got a kind of a liquid here, and it's going to boil and turn into a gas. And then we're going to run that gas into, and it's going to pick up heat from the outside. So this is going to be a fluid that boils at a low temperature. Let's say it's 20 degrees Fahrenheit, and the outside temperature is 35 degrees Fahrenheit. Then the 35 degree air will boil that fluid. It boils at 20. It's going to pick up heat from the air, and then going to run it through a compressor. And that compressor is going to compress. It's going to be a low temperature, low pressure fluid here and a high pressure fluid here, and it's going to increase the temperature of it. So the temperature now is hotter than the temperature in your house, and you're going to then be able to take this fluid here this gas, and you're going to condense it. And when you condense it, you change it from a gas to a liquid. It's going to give off heat, and it's going to condense. It's going to be hotter than the temperature in your house. Let's say you want the temperature in your house to be 75. Maybe this is 95, and it's going to condense and change from a gas to a liquid. And now we've got a liquid under high pressure from the compressor. The liquid's under high pressure, and it goes to this expansion valve where it expands, goes from a liquid to a gas, just like in a aerosol bottle. When you take the aerosol, press on the nozzle, and the aerosol comes out of the can, the nozzle will get quite cold. Try this sometime. And essentially, what you're doing is then you're figuring a way to repressurize that expanded gas back into the can again and run it through the nozzle. That's one way of thinking about this. But so then the high pressure liquid expands and becomes a gas, which then goes out here and condenses into the high pressure liquid becomes a gas and a liquid, comes out here and picks up heat and goes through this whole process again. Sorry if that was not as clear as it could be. Let me try it with the heat pump cooling cycle. So in this case, what you're doing is you're taking hot heat from inside your house at 70 degrees, and you're trying to dump that heat outside when it's 100. So you're trying to move the heat in a direction it doesn't want to go. So let's start in your house where you've got the expansion valve, and you've got a higher temperature, excuse me, a high temperature liquid. It's gas that's hotter than it is in your house. And what's going to happen is, no, I'm sorry, that's wrong. This is going to be a low temperature gas and liquid, and it's going to come in here and it's going to evaporate and pick up heat from inside the house. So this is going to evaporate at, let's say 50 degrees, and your house is 70, so it's going to take heat out of the air in your house. It's going to evaporate, and then what you're going to have coming out of here is a gas that has, this was a liquid coming in, and it's going to change from a liquid into a gas. And then that gas is going to come out here, go through a compressor, get compressed from a low pressure gas that has heat in it from your house into a high pressure, high temperature gas, and that's going to be, now it's going to be hotter than it is outside here. So let's say outside it's 100, maybe this is 120 or 150, and so then it gives up its heat to the outside, And when it gives up its heat, it's going to condense back into a liquid. And it's going to go as a liquid down here under high pressure to the expansion valve, expand and cool off. And now it's partly a liquid, partly a gas. And it's going to come down here, and then that liquid in there is going to boil and pick up heat from from the room, and going to turn into a gas. All the liquid's going to turn into a gas and absorb energy as it changes phase from a liquid to a gas. You know, it boils, it absorbs energy, and then the whole process starts again. And so, again, you'll have to kind of think about this for a little bit, and I'll try to go through this in the classroom, but that's the basic cycle for heat pump or an air conditioner or a refrigerator. That's how one way in which you can move heat from where in the direction it doesn't want to go, from cold or from warm, excuse me, floor from cold to warm. Now there are other ways of of making this process work that don't involve a compressor and electricity. There are ways in which you can use heat to drive this process, and we're not going to get into this in detail, but if you have a process that just requires heat to drive it, to be a heat pump or an air conditioner or a refrigerator, then you can use all kinds of different sources of energy to drive the process. You can use solar energy to drive the process to make air conditioning. And this is a absorption cycle. No, excuse me. This is the same cycle. Let me just look at something else here. Okay, this is just another way of looking at this. You put heat into the evaporator. You boil the liquid, and this is now a gas. Gas goes into the compressor, becomes a this is now a low pressure vapor. It goes through the compressor, it becomes a high pressure gas, and it's hot. It dumps its heat out someplace where you want to get rid of it. Then as it dumps its heat, the high pressure gas then becomes a high pressure liquid. It condenses, comes through here, goes through an expansion valve, and becomes a low pressure gas liquid, where then it goes to a place where it picks up heat, a radiator of some kind, where it picks up heat and boils and becomes a low pressure vapor, which then gets run through the compressor and goes through that cycle over and over again. Now let's look at what I started to mention earlier, a system where you drive the process with heat rather than with an electric driven compressor. And how this works, this is called absorption cycle cooling, and it's how gas refrigerators work, like in an RV or a boat or in a remote home. And you can use just a little bit of heat to drive this. A little bit of heat in here can move a lot of heat from a cold to a warm place. And so you start off with water dissolved in ammonia dissolved in water, and the ammonia dissolved, you put some heat into that and start to heat that up. And when it goes up here to this separator, what it does is the ammonia boils out of it. The ammonia goes out of it. It comes up here, and then this is set up at a temperature which it condenses and picks up heat and takes heat out of the system. And then it rejects heat like to the outside somewhere. And then this is a cooling situation. And then it comes back here, goes through the evaporator where it picks up heat from inside the refrigerator, and comes down here, and then the ammonia is absorbed back into the water, and then the whole process starts again. And that's a little bit of hand waving there. Again, I don't really have time to get into the details of how these work, but you get kind of the rough idea that the whole process, rather than being driven by a compressor, is driven by a little bit of heat into the system, and it drives this ammonia absorbing into the water, in and out of the water, coming out of the water, and then absorbing back into it. That's why it's called absorption cycle cooling. And again, I can talk about this more in class, or we'll get into it more in the next course. But this is this particular cycle of refrigeration or heat pump is amenable to being driven by solar. There's also many other kinds of cycles that can be for cooling and heating. We're not going to get into those here, but there are things like swamp coolers in really dry climates where it's really hot, like in the desert. You can run air across a moist fabric surface, like almost like a wet towel or a wet sponge, and that dry air will evaporate the water, and when that water evaporates, it'll absorb a tremendous amount of heat and it'll cool the air off. This only works in areas where it's not humid, but it can use maybe 1/10 the energy of a conventional air conditioner to do that. So swamp coolers are another way. Desiccant coolers, again, I don't have time to get into the details of how they work, but this is something we could consider at the Sustainable Living Center to have less dependence on the heat pump for cooling in the summer, because we've got this huge solar thermal array and we could use that for cooling. Now I want to talk just a little bit about high temperature geothermal. And so this is the situation. We talked about low temperature geothermal and heat pumps earlier. Now we're going to talk about the heat that's deep within the earth, maybe several kilometers in the earth. And let's just watch a short video on how that works.
The deeper you go into the earth, the hotter it gets, reaching between 4,000 and 5,000 degrees Celsius at the core, 6,000 kilometers below us. With every kilometer you descend, the temperature typically rises by 25 to 50 degrees Celsius. In the 20th century, man harnessed some of this vast energy by building geothermal power plants, which used steam from heated water deep underground to drive turbines and generate electricity. The first ever geothermal generator was tested by Italian Prince Piero Ginori Conti in 1904. It successfully lit 4 light bulbs. Geothermal electricity plants were built near tectonic plate boundaries because high temperatures could be accessed much closer to the surface. Today there are geothermal power stations in 24 countries, with the US by far the biggest producer. Worldwide, geothermal generates enough electricity to meet the needs of 60 million people. Once built, the plants provide cheap, reliable and virtually emissions-free power. Recent advances in technology are making geothermal a viable prospect beyond tectonic areas. This has launched the idea of converting some of the world's millions of disused oil and gas wells into geothermal power stations. A recent development is pipe-in-pipe technology. Water flows down an outer pipe, is heated, and then flows up an inner pipe. The hot water is then used to vaporize another fluid, which drives a turbine to generate electricity. Since drilling is expensive, around half the cost of setting up geothermal plants, this could be the key to cheap, clean power. Even operating oil fields could generate geothermal power, using the hot water, which is a byproduct of the extraction process. Oil fields commonly produce 10 to 20 times more water than they do oil, a vast resource that's currently wasted. In Texas, researchers have mapped out geothermal potential across the state, helping to indicate which disused wells could be worth re-entering. Although these would only make for miniature power stations, the numbers are huge. There are an estimated 2.5 million abandoned oil and gas wells in the US alone.
So there's a little bit about hot rock geothermal energy, and let's look a little bit about this idea that Google has been promoting of deep geothermal, where just about any place on, what they were talking about mostly in the previous video about deep geothermal is located in very special circumstances around the Earth, where the Earth's temperature is quite close to the surface. Even with those oil wells they were talking about, there would be places where it's fairly close to the surface. Google is throwing out the idea that now that we have the technology to drill many kilometers into the Earth, almost anywhere on the Earth we could drill deep enough into the Earth in order to get the energy we might need to make electricity. So let's hear about Google's plan.
planet is heating up and energy prices are rising, the need for cheaper, renewable energy on a vast scale is greater than ever.
It's a crisis. It's not too late. I have extreme confidence in the ingenuity of people if they recognize what needs to be done. There's no single answer. There are many, many answers.
One answer, with the potential to be both utility scale and cheaper than coal, lies deep in the Australian outback. The world's first commercial enhanced geothermal system is underway. Geothermal energy has been used for over 100 years to create electricity from hot water and steam coming from deep inside the Earth. Geothermal has primarily been developed in regions along continental plate boundaries such as California, Indonesia, and Iceland. Now, Enhanced Geothermal Systems Technology, or EGS, could extend the potential of geothermal energy to almost anywhere on Earth. Here's how EGS works. A well is drilled several kilometers into the Earth's hot crust. Water is injected to fracture the rock, creating thousands of small pathways for water to flow and be heated. The hot water and steam are piped to the surface to power a turbine, generating electricity. The water is then recycled back into the hot rock in a continuous loop.
The reason enhanced geothermal is exciting is because it's a reliable form of energy.
It's providing baseload continuous power with high availability. It's essentially emissions-free and therefore carbon neutral, and it has this distributed indigenous nature so that it's not just in the southwestern parts of the U.S. It is extendable and scalable on a national scale.
The Earth is going to be hot. You can bank on it.
In the U.S., on an annual basis, we use about 100 exajoules of energy, all primary energy for all of the homes we heat, the buildings we supply electricity to, all our transportation use. And if we added up the geothermal resource for the whole country, we come up with a number which is about 14 million exajoules.
You can consider the energy source effectively an unlimited supply.
We have to improve the amount of fluid that we can pump through this reservoir to get much more access to that stored thermal energy in the rock. So increasing productivity and decreasing drilling costs simultaneously makes the overall enterprise much more attractive.
EGS could provide renewable power 24 hours a day, 365 days a year, and on a large scale around the world.
Once you get large, and you do this large on a national basis, then the costs will come down naturally.
Dig deeper at www.google.org/EGS.
So there's another, something else is being brought to us by Google, whether we want it or not. And again, I think deep geothermal has a place. It's going to be inherently centralized, inherently expensive. So I think as a complement, to solar and wind power, so that you can provide that steady kind of base load power that you might need, but we could also get that energy from biomass in cycling in the biosphere with solar energy and biomass. Might be much less expensive, and it might provide more employment opportunities if we went that way. So I think it's something we need to consider, but again, I think you have to kind of put your critical thinking hat on and think through, is this an approach that creates a world that we all want to live in. And so that's the end of the discussion about geothermal energy.